In this problem, we start out with two immiscible liquids, water and normal octane, at 1 bar pressure, and we state that they're in the liquid phase, no vapor is present at 85 degrees C. And then we're going to heat them up at constant pressure to 130 degrees C, and what we want to know is what's the partial pressure of water as a function of temperature. And we're given at 1 bar pressure that the normal boiling points of water and normal octane are 100 and 126 degrees C. So the best way to approach this problem is to first look at what a temperature mole fraction diagram would look like for this mixture. So let's stop and look at this diagram. So we can label some points on the diagram, and this is pure water. And we know that its saturation temperature is 100 degrees C. So that means we have water. Higher temperature is going to be vapor, lower temperature liquid. Here is pure normal octane, and its saturation temperature is 126 degrees C, so right here. Now at our starting temperature, 85 degrees C, we have just liquid, no vapor present. And so as we change the temperature, so if we have pure water with no normal octane, now we mix water and normal octane, keep the total pressure the same. That means the partial pressure of water decreases, and since we have liquid water in equilibrium, that would mean the temperature decreases. So we have some sort of curve that looks something like this, where the temperature decreases, that's the saturation. Pressure decreases, and likewise for normal octane. So we have some other curve, and I'm just drawing this approximately. We know we have only liquid at 85, so let's assume that around 90 degrees is where we start getting vapor, at least if we're at this mole fraction. So this is just a very rough drawing of what a temperature mole fraction diagram looks like for two immiscible liquids. Here liquids, here vapor. Here is normal octane liquid plus the vapor. Of course, the vapor contains both components. Here is water plus, so liquid water, plus the vapor that contains both components. And the problem says we start 30% water, 85 degrees C. So we start here. I'm going to raise the temperature. So as we raise it to 90 degrees, we just start now at 90 degrees to form vapor. Looks like the mole fraction maybe 0.68, 0.69. And then let's say we raise it to 110 degrees. Now the mole fraction in the vapor water is 0.5. Well, we're interested in the pressure. So the pressure, of course, the partial pressure of water is the mole fraction of water times the total pressure. So the partial pressure of water 100 degrees would be 0.5 times 1. And here it would be about 0.68 times 1. If I get to 110 degrees C, it looks like the partial pressure is maybe 0.33 bar. And 120 degrees, the partial pressure is 0.3 bar. 30% water, 70% normal octane. So we want to then plot these partial pressures versus temperature. Well, here's the graph. We're going to plot partial pressure versus temperature. At 90 degrees C, we get the first vapor forming. Below, we have no vapor. We have no partial pressure. And then this number, partial pressure around 0.68. So if I can draw a vertical line, about 0.68. Then if we look at some of the other values like 100, we read that off, it's somewhere around here, 105. I didn't show that on the graph, but if we go back and look about here, and about 112 or 13, we get down to 0.3. And then now we only have vapor, so the mole fraction doesn't change. Partial pressure doesn't change because the total pressure is constant as we raise the temperature. So then a rough plot would look like so of the partial pressure of water versus temperature. We, of course, could generate an exact plot by using the Antoine equation and calculating the saturation pressure at these various temperatures. But this gives you a pretty good idea of the behavior we'd expect as we raise the temperature on this mixture. Well, here's an exact plot of the temperature versus mole fraction of water was generated using Antoine equations. And then from this plot, from those equations, we can generate accurately what the water partial pressure versus temperature looks like.